Here at the Hubble Space Telescope. You're about to get a tour from Jim through the control center. It's pretty cool back there. You'll be able to see a lot of fun things. I just wanted to greet you all and welcome you, but also I wanted to let you know that this April, Hubble is celebrating its 30th anniversary in space, and we're doing a lot of cool things, and a lot of that is social media stuff, and we want, if you're here and you're excited about NASA already, we want to get you all involved. There's going to be a bunch of fun things, and you can find them on our website at nasa.gov/Hubble. There's a anniversary page there where you can find everything that's going on. But also, if you just follow us on social media at NASA Hubble, it's all there too. So just we want you to follow along. We want you to celebrate Hubble with us this spring and all year, really. So that's about all I wanted to let you know. If you have any questions on that, feel free to ask me. I'll be tacking along through your tour, and I'll turn it over to Jim.
Okay. So you're standing in front of a 1/5 scale model Hubble. It's the real thing. It's about the size of a school bus. It's 43 feet long by 14 feet wide, the main body, and it weighs over 27,000 pounds. I'm just going to answer a couple quick questions that we typically get. How do we turn Hubble? So the way you turn that thing, there's no thrusters on board or fuel or anything like that. The way you turn it is with something called reaction wheels, and they use the law of physics. For every action there's an equal and opposite reaction. So we have these 2-foot wide wheels that are 100 pounds each, and spin them one way and Hubble's going to spin the opposite direction. So there's 4 of those, and so I can pick any 3 and turn Hubble in any direction I want. Because it's so big, it moves pretty slowly. It moves about the speed of a minute hand, so if you want to turn 90 degrees, it's going to take you about 15 minutes. Now we have a second way of doing it too, which helps, but it's not the primary way. But it's these bars here. They're 8 feet long and 3 inches wide, and have metal coils inside, and they fire enough electricity, they become magnets, and they use the Earth's magnetic field to pull or push Hubble in a particular direction. So those combined with the reaction wheels is how we turn Hubble. Now, we're going to show this to you because there's a picture behind here of Hubble in space, one of the last ones ever taken in 2009. It shows the Earth's atmosphere. It's a thin layer of atmosphere, and that's bad if you're an astronomer on the ground. But if you can get above that atmosphere, you get much, much higher resolution, 10 to 20 times. So think of it as taking a picture of something with a 1 megapixel camera, and then comparing it to something with a 10 to 20 megapixel camera, and the significant resolution difference. So Hubble's 340 miles up. There's still a little bit of air molecules up there, but not enough to impact us from that perspective. Okay. Another thing is, just real quick, is we have to keep Hubble really, really steady. So we have a requirement that when we take a picture, you don't want to do this with your camera, or it's going to be blurry type thing. So we have a requirement that we have to be able to keep it such that if we put a pointer on Hubble and taped it and shined it, we'd have to shine it on the dime, and not just on a dime, but on the head of the president on the dime, and keep it on there for however long we take the picture. Mm-hmm. And if Hubble was here in Washington, D.C., that dime would be on the Empire State Building in New York City, and that is our pointing stability requirement. Okay? All right, one other quick thing before we go in. Another capability you have by being above the Earth's atmosphere is you can see different wavelengths of light that you can't see from the Earth because the Earth's atmosphere blocks it. One of those is ultraviolet light. The other is infrared light. So this is a famous picture taken by Hubble of the Eagle Nebula. It's called the Pillars of Creation. The one on the left is taken in visible light like your eye sees, and the one on the right is taken in infrared light. So you can see the difference. You can see how many stars there are, tens of thousands of them, that are inside that cloud and behind it, and you never have a clue existed if all you did was take a look at it at visible light. So that's why we like to have a telescope up in space that can see that light that you can't get from the ground. All right? Okay, so let's go ahead in. You're welcome to ask questions along the way.
So how does it lock to a particular star so stable? Is that reaction wheel like you said before?
So there's a system called a fine guided sensor, and what it does is it finds guide stars and kind of locks onto them, and it does that through interferometry. But in English, what that means is how it really works is it's splitting the light of the star in this direction twice, and then in this direction twice. So if you split the light from the star and you measure that light, how much do you have, then you get a 50-50 cut if you're dead on the star. So 50% of light goes this way and 50% goes this way. If it's 51:49, then you know you're starting to move off the star. If it's 52:48, you moved even further off the star. So the computer on board says, hey, how far am I off the star? What direction? From the fine guidance sensor, that interferometer, and then it turns the reaction wheels to adjust to keep it on target. So that's how we keep that as close to on target as we can for as long as possible.
Thank you.
Okay, this room in the back, so you can look in and see this. But what they're doing here is they're monitoring the spacecraft and making sure that nothing gets too hot or too cold, or the voltage levels aren't right, and it's following commands. What happens is we upload 24 hours worth of commands at a time to the onboard computer, and it kind of just goes off and does its thing. The onboard computer, that's an equivalent to it in that black box that's right in front of you. That has an Intel 8486 chip in it, which was designed in the 1990s. And what I'm going to do is kind of compare that to your iPhone 11s right now. So, your iPhone 11 has 6 processors in it running simultaneously, and that has 1. Those 6 processors are running at 2.6 billion cycles per second. That's running at 25 million. Your iPhone has 4 gigabytes of RAM, meaning it's memory that you load your operating system and apps into. This has 2 megabytes. And then your iPhone, you can get up to ½ terabyte in terms of memory for all your movies and stuff. This has 1 megabyte. So we don't save the images in that to it. We have another device for doing all the data. But we still only use about 60-some% of the computing capacity and 70-some% of the memory on this computer. So we're very, very efficient. And because we have this computer, which was the upgraded computer that the astronauts put on in 1999, the original one was a 1 megahertz with 72K of memory. Now we can automate things on board, and so now it checks itself. So normally people are not in here, because what happens is that we have an app, specialized app capability on our iPhones. That's through secure software. We can take a look at some of the telemetry, just like they're doing in there right now, in case there's a problem. If there is a problem, the onboard computer sends an error message to the ground. If there's a problem that the ground system notices by looking at all that telemetry, and there's over 10,000 telemetry points that we can get at any given time, and they'll say, hey, something's not right, and it'll send a text message to us. And then we have so many minutes to reply to the text message on our phones, or it says, hey, they have their phone turned off, I got to talk to somebody, and it goes on to the next person, and it's call list. And then once they call us, or once they realize they've contacted us, we can then take a look online and kind of figure out if we need to come in or not, what's the problem is. The board on the right is kind of showing the types of data that they're taking a look at, and the plots and things. That circular plot is trying to circle around a guide star by the fine guidance sensor and trying to lock onto it. And that the bottom plots are showing you when you're in sunlight, when you're not, because it's showing you current, and that with the batteries, so we know when we're charging batteries and when we're discharging batteries. They worry about things that are on the plot on the left. That's a plot we put together for every hour of the day. We worry about when we're in daylight or not. We also worry about something called the South Atlantic anomaly. It's an area above the South Atlantic Ocean that has high electromagnetic radiation, so we actually power down some of our detectors and that so they don't get harmed by it. We're worried about which instruments are on and whether they're working properly. And then of course the bottom 6 are all our communication contacts that we have with Hubble. We communicate mostly through a communication satellite that's 22,000 miles above Hubble. So we beam our commands up to it, and it sends them down to Hubble, and then Hubble sends the data up to it, and it sends it back down to Earth, etc. So there's different types of contacts, whether we're sending data, whether we're sending commands, and those are telling us at what times we can do.
So do you turn off those instruments every hour and a half, because it takes hour and a half for one round, right?
So what we do is we only use one instrument typically at a time. We sometimes use 2, but they look at different areas of the sky. There's so if you can kind of think of the field of view of Hubble as a dinner plate, okay, round dinner plate. Every instrument has its own part of the dinner plate that it can look at. So depending on what the scientist wants to do, and for that given moment, we've scheduled it such that one instrument will be on. Now, as you go around the Earth, what happens is the Earth blocks you sometimes from seeing it, so we don't take data during that time. And then as we come back around, we acquire those guide stars again and take data again. So it all depends on what you're looking at. Sometimes you're looking at what we call the continuous viewing zone, meaning you're pointing up, and the Earth never blocks you, so you can always stay on it the whole time. It just depends on where their target is. Where we do anomalies, meaning if something's wrong with the spacecraft, so we pull people in, and you can see the little blue signs above them. OM stands for Operations Manager. 486 FSW is flight software for main computers, flight software people. PCS is the pointing control system that uses the reaction wheels and that. So we bring all the experts in. They can all take a look at their data and figure out what's working, what's not working, why, and helps us figure out how to resolve the anomaly and get us back on track to doing science again. We also use this for testing purposes, different types of testing. So before we do anything on the spacecraft, we always test against a very high fidelity simulation capability that we have on the grounds here at Goddard, and make sure that everything works against it before we ever do it in space. So that's kind of a risk mitigation thing we do to make sure that we don't have an uh-oh moment. Right? So they're in there now probably doing some testing on the ground. But I wanted to show you some other things that are of interest to people. If you look at the display cases in front of you, and I'm going to start with this particular one. The display cases show hardware that we returned from Earth and some of the tools that the astronauts used. The astronauts went up and serviced Hubble 5 times on the space shuttle. And so they upgraded it, fixed things that were broken, did standard maintenance, just like on your car, you would eventually replace your battery. We replaced the batteries the last time we were up there, et cetera, so the Hubble can last as long as possible, and also take advantage of new technology, so that way, every time we went up, it was even better than the time before. In this particular case, this is a picture of an instrument that has about the size of a large refrigerator. It has what's called a spectrograph in it. A spectrograph breaks the light into a rainbow, and you can take a look at that rainbow, and by looking at the bright lines in the rainbow, there's certain stripes that will occur. You can determine what elements a particular object is made out of. The problem was that a power supply went, so just like on your laptop, the power supply goes, you replace it, and you're back in business. A little bit more difficult when it's up in space. This particular card was the power supply. This is what it used to look like when we launched it, before we took off all those little boxes to figure out why it failed. Those boxes are power converters. They're converting power from one voltage level down to another voltage level. We took the lids off of them to take a look inside, and you can see there's like red dots, and this is the lid, and if I flip it over, it matches the red dots that are inside the box, so you can kind of think of it as glue for the lid. But what happened was that when we launched into space, there was air, and the air expanded, which caused the lid to bow up, and then it pulled on those components, and after 7 years of that stress, a solder joint failed, and one of those components failed, which then cascaded down the line and everything failed. So we wanted to be able to bring this back to life. STIS is this is Space Telescope Imaging Spectrograph, or STIS. It's extremely important to us, because when you look at the results of Hubble on all the exoplanets that we're looking at to see what's in their atmosphere and that, this is the instrument that we're doing it with. So we created this particular device for the astronauts, this blue device, so that way we can take the card out and put a new card back in. We didn't want the astronauts to touch the card because there's sharp parts to it. We don't want them to accidentally slice their glove. We also didn't want the astronauts to accidentally break something on the card, on the new card, because that would mean it wouldn't work. So we created this claw, and this is called a card insertion extraction device. Claw grabs it, and if you can kind of think of this as the instrument on its side, here's the card, and then this is the claw on the instrument, and then you see the 2 silver legs on either side, or my thumb and my middle finger. So what happens is, as you turn this knob, it pushes the legs out, which then causes it to pull the card up and out. Then you put the new one in, you extract the legs, and it pushes the card back in, such that all these hundreds of pins are perfectly aligned to go in the right hole the first time. So we do that not only for safety purposes, but also for the purpose of efficiency. We don't want the astronauts to be out there any longer than they have to be because it's a dangerous environment. We're also held to 6-hour spacewalks at a given time. So we want to keep them safe. We want to do as much as we can with them during that time period. So we create these types of devices so that way they're as efficient as they can be. Okay. Down here real quick, this is a power screwdriver. Okay, now you can say, why don't we just go to Home Depot and buy a power screwdriver? They don't work in space. The particular materials are made out of carbonized in the vacuum of space, and therefore they'll run for about 3 or 4 minutes, and that'll be it. So we have to create a special one with special types of materials and that so that it'll run as it should. They put the bits on the end. These are screwdriver bits. You can see the bits go into a bit caddy. If you notice, there are these thumb tabs with posts on it on the bit caddy. So you can put the bit in, you can push the thumb tab up, then the post will go in the hole on the side of the bit and the bit will not come out. So therefore it can't float out, and then they're required to engage it on the end of the screwdriver before they push down the thumb tab to release it. So therefore it's always either in the bit caddy locked or it's locked onto the end of the screwdriver, and therefore they can't lose a bit. They're also color coded, and we have devices that we use where things are color coded such that way they know exactly for that particular screw which screwdriver they need. They just go by the color and they can get it right away as opposed to looking for a particular size screwdriver of a certain head. Okay. One other quick example for you here. This is another instrument. Also had the power supply go, but you couldn't get down into it. So what they did was they decided that they would take the cards out. There were 4 of them that had to come out, and they would put 4 identical cards back in. And the only difference was that instead of being able to get power from the bottom, they were rewired to get power from the top, and a new power supply was mounted on the external part of the instrument and plugged into the cards, and then the cards fed the rest of the instrument its power. To do that, we have, if you notice the right arm of this astronaut, there is a metal grid, a goldish silver metal grid that had to be cut off. So we created a grid cutter tool for the astronauts by turning those bolts. You can see on the back there are razor blades that come out and cut through the metal grid. It's double-sided tape to the metal grid, so that way they just grab those 2 knobs. They never get their gloves close to the cut metal, and they can put it safely into a container. Once they get that off, underneath that you can see there's a black panel that's held on with screws, so we have to get that off. The black panel is underneath the silver device. The problem is, as you can see with the screws that were taken out, they would just float away. So we have to make sure we capture them, so we created a fastener capture plate. By putting this on with double-sided tape again, you notice there's holes in the silver and the clear plastic, right above it where every screw hole was. Those holes are big enough for the screw bit to get in to screw out the screw, but not big enough to allow the screw head back out. So as long as you leave it double-sided tape, the screws are stuck between the black panel and the clear plastic. Once they're done, they take this off, again, put it in a bag, and they're done. And then they replace all this with a module that has 4 cards already in it. They just stick it in and turn the handles, and it's locked in, and they don't have to worry about putting all the screws back in. So there's a different way of locking it on. And then this device is the same as that device, except for there has to be, you can see the claw, and there's 2 legs on either side that go up and down, but it has to be such that we can get 4 cards out there on different locations, so there's a handle to move the claw to the 4 different locations. So these are the types of things that they come up with to be able to service the Hubble. So let's go over here. A tape recorder, for those of you who remember a tape recorder. So, and you're welcome to come closer if you want. So this tape recorder is how we record data on Hubble. When we first launched it, it flew for 7 years. There were 3 of those on board. If you notice, a little yellow sticky has an arrow pointing to where the tape came off the rollers. That'd be problematic if it happened in space. There's nobody up there to put it back on the rollers. The good news was it didn't happen in space. It happened after we brought it down and we put it in our simulator, and then it came off. Now, with that in mind, we knew that type of thing was going to happen. The other thing we knew that was going to happen was that detectors were getting better. So when Hubble was originally launched, it had a 2.6 megapixel camera. We now have 2 16 megapixel cameras, so the file sizes are that much more bigger. So we wanted to be able to handle larger amounts of data and faster than the tape recorder. So we replaced this with basically what's equivalent to a USB stick. All right, so it's got solid state memory, and except for it's about this big, but that's all it is. It's solid state memory. So therefore, there's no moving parts to break. It holds 10 times as much data as this guy. It can read and write faster than this guy can, and it's also can read and write at the same time. So there's all kinds of advantages to the solid state memory. Now, one other note, last thing I just wanted to show you real quick is this is a gyro, and I'm not going to get into how the gyro works other than to say that one of the gyros was giving a problem on board in 1993 when they first went up to service Hubble for the first time, and they weren't sure if it was the gyro that was the problem or whether it was the control unit for the gyro. So they brought them both back, and what ended up happening was they realized this had a bad capacitor. So they changed out the capacitor, brought it back up to flight status, and we were ready to fly it again in case we saw that same problem on any of the other controllers. But it never did, so now it just sits in a display case. A lot longer. We're hoping that we can be here for at least to the late 2020s or beyond, because we still have redundancy in all of its critical systems. And after 30 years, we've had over almost 1.5 million observations to date, and hopefully we're going to get that many more. Okay?
Thank you.
All right.
Appreciate
Heading
it.
back this way?
Yes,
Okay.
so the next group.
Fire a big tectonic plate in the Pacific Ocean. I need to fix this 360 camera on top of my van. These Rocky Mountains stretch from New Mexico all the way to the British Columbia for around 3,000 miles. It feels like out of this world here. I chose Denver, Colorado as the starting point because